Hey, this video is going to go over the minimum number of degrees questions in the Regents review packet for geometry. So this question, or these questions are basically asking like, what's the smallest number of degrees that you can turn a shape and have it still look like that shape? So like this doesn't apply to something like a circle, like this nice plate I have here. Because if you turn this, it's still going to look like a circle regardless. However, if I take this really nice looking calculator, but if I have this like old calculator, but if I turn it, it's going to take a whole 180 degree rotation for it to like still look like a calculator. Same thing with something like the letter H, and I know this isn't perfect, but pretend like this straight across. Let's look at the back because the back is all black instead of designed. So if you look at this H and if you pretend like it's perfect, right? If you turn it 90 degrees, it's not going to look like an H anymore. You got to turn it upside down, which is 180 degrees for it to look like an H again. Now, because a lot of shapes are regular, meaning like the sides are all the same, there are some patterns that you can come up with if you have a regular polygon. So basically one thing that you can do to find the minimum number of degrees for any regular polygon, which means one where all the sides are the same. All the sides are equal. So what you can do is you can take 360 and divide it by n, and n I'm calling the number of sides. And this will give you the minimum number of degrees you can turn it. So when it says a regular pentagon is rotated about its center, a pentagon has 5 sides. And if I drew this perfectly, all the 5 sides would be the same size. It's rotated about its center, which is like this. What's the minimum number of degrees needed to carry the polygon onto itself? Carry the polygon onto itself just means like, when does it look like a pentagon again? When does it look like itself again? Now, if you connect all the corners to the center, you're going to create, in this case, 5 different angles because it's a pentagon. All these angles are going to be the same, and when you turn it, that number of degrees, it's going to still look like a pentagon. Like if I drew this perfectly, it would look like a pentagon. And then I have another pentagon like this, where the top of the pentagon would be here, and they would all be perfect though. I did not draw this perfectly, but you can imagine. So what I'm going to do is one full turn is 360 degrees. But I'm going to take 360 and I'm going to divide it by 5 because that's the number of angles I've created from this pentagon. So 360 divided by 5 is 72, which means that 72 degrees is the amount in each of these turns. So I've got 72 degrees. That would be the minimum number of degrees. Now, if I wanted to find the angle that's like from here to here, that would just be 2 of the 72s together. 72 plus another 72 would be 144. 144 would also work, but it's not the minimum number of degrees. If I kept going, there would be another 72 degree angle here. So that would be 3 72s. So you could do 72 times 3, or we could just add 72 again, which would give us 216. And I could keep going around. There would be another 72 degree angle here. I could add 72, and that would give me 288. And then I could add 72 one more time since I've got this last angle, and that adding 72 is going to bring me back to 360. That's going to be the full circle. So this one, the first one you get when you do the division, if you have a regular polygon, that is your minimum number of degrees. 5 says which regular polygon has a minimum rotation of 36 degrees about its center that carries the polygon onto itself. So we can just test this out. So pentagon, we've already done 360 divided by 5. That's 72, not 36, so that's out. Octagon has 8 sides. So 360 divided by 8 is 45, which is not 36. Nonagon is 9 sides. 360 divided by 9, which is 40. Also doesn't work. Decagon is 10 sides. So 360 divided by 10, that is 36. Now, if you didn't have these answer choices and you wanted to figure this one out, you could create a little equation. You've got this, 360 over something is supposed to give me an answer of 36. Now you could put this over 1 and you could cross multiply. 36n equals 360. Divide both sides by 36 and you get n equals 10. So you could solve it, it is possible. Now this formula works only for regular polygons. Not all of these are regular. This one, number 1, says which polygon has a minimum rotation of 180 degrees about its center to carry it onto itself. That means the smallest rotation to make it look like itself again is upside down, 180 degrees. Now, square and regular pentagon, these are regular figures because all the sides are the same. So we can use this formula, 360 divided by 4, that's 90-degree rotation. That makes sense, right? Because all the angles are 90 degrees, but also the diagonals are perpendicular. So if you turn them, you know, it's going to look like a square again. We've done pentagon as shown up on multiple questions, but again, you could create your angles this way, and they're all equal angles. That's the nice thing about regular figures. 360 over 5 is 72, so that's not right either. So now we're down to a rectangle and an isosceles trapezoid. A minimum rotation of 180 means it's got to look the same upside down. Only one of these looks the same upside down. That's number 1, it looks like a rectangle upside down. This one doesn't look the same upside down. It actually doesn't really look the same any way you put it. This does not have, it's just 360. Like it only looks like itself when you rotate it 360 degrees. All right, on the next page, this one got misplaced, so we're gonna skip that one, but the rest of them are okay. 6 says which regular polygon would carry onto itself after a rotation of 300 degrees about its center. Now notice this one doesn't say minimum number of degrees, it's just saying 300 degrees. So it's kind of like, we gotta list out all of the options and then see which one has 300 degrees on it. So the first one is a decagon. A decagon has 10 sides. So 360 divided by 10, that's 36. So if we start listing out, counting by 36, so 36 would work. And there's gonna be 10 angles because there's 10 sides. So 36, and then adding another 36, we get 72. Adding another 36, we get 108, then 144, then 180. That's 5, we're halfway through. 216, add another 36, 252, add another 36, 288. Now, if we add another 36, you can already tell 300 is not gonna work. We get 324. And then if we add another 36, we'll be back to 360. 1 is out, 300 is not on the list. So let's try nonagon. Remember, a nonagon is 9 sides. 360 divided by 9 is 40. 40 is a little easier to count by. 40, 80, 120, 160, 200. And we're going to have 9 of these. 240, 280, nope, 320, 360. So that's out. 300 is not on the list. Octagon is 8. 360 divided by 8 is 45. So we're going to count by 45s. 45, 90, 135, 180, 225, 270, nope, 315, 360. So it's got to be the hexagon. Let's try it. 360 divided by 6 for hexagon, that's 60. Count by 60s. 60, 120, 180, 240, 300. There it is, 360. So notice decagon, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 angles that work. Nonagon, 9 angles. Octagon, 8 angles that work. Hexagon, 6 angles that work. Those are for regular figures. All right, 3 says, what's the minimum number of degrees that a regular hexagon must rotate about its center to carry it onto itself? Hexagon is 6 sides, so 360 divided by 6, 60. 15 says, which regular polygon will carry onto itself after a rotation, a 135-degree rotation about its center? So regular polygon, so triangle, 360 divided by 3, that's 120 degrees. So we got to count by 120. 120, 240, right? You don't actually have to count by 120 in your head. You can just keep adding on your calculator. 120 plus 120 is 240. 240 plus 120 is 360. I'm looking for one that has 135 on it. Now, pentagon, 360 divided by 5 for a pentagon. That was 72, and we can count by 72s. 72 plus 72, 144, plus 72, 216, plus 72, 288, plus 72 is 360. That's no good. Hexagon, 360 divided by 6 is 60. 60, 120, 180. This isn't working either. So it's got to be the octagon, which is up here anyway. 360 over 8. 45, 90, 135. There it is. And you could keep going, but it has it on the list. A regular nonagon has a center point P. What degree of rotation about point P will carry the nonagon onto itself? Nonagon, 9 sides. You got to memorize it to get this point. 360 divided by 9 is 40. So we're going to count by 40s here. It doesn't say minimum number of degrees, which is why 40 is not one of the options. So we're going to count by 40. 40, 80, plus 40 is 120, plus 40 is 160, 200, there it is. We could keep going, 240, 280, 320, 360, just to make sure we didn't make any mistakes, but we're good. All right, that's minimum number of degrees.